All right, so now that we've learned about how to figure out molecular geometry in 3 dimensions, we could talk about bond polarity. If we have used VSEPR theory to deduce molecular structure, we can assess whether the molecule is polar or not. And just as a review of a concept from the bonding chapter, whenever you have a bond between elements that have different electronegativity values, that bond is said to be polar. Okay, so a difference in electronegativity between bonded atoms gives rise to a polar bond. Now, okay, so that's bond polarity. Now let's talk about this concept of dipole moments. In order to have a dipole moment, two requirements must be satisfied. A molecule must have polar bonds. Okay, so it must have bonded atoms with different electronegativity values between them. But that's not enough. It must also have an overall asymmetrical charge distribution. If both of these requirements are met, that molecule can be said to have a dipole moment. Another way of saying it, uh, another way of saying it, another way to describe it is that it's a polar molecule. So the molecule is overall polar, not just a bond in the molecule, but we could say that the molecule is polar. So any molecule that has a dipole moment is polar. Molecules that do not have dipole moments are nonpolar molecules. So let's go over some examples. Let's start very simple with diatomic molecules. Let's say that we have the HF molecule. Now, we know that hydrogen is a very electropositive atom. Fluorine is very electronegative. So this diatomic molecule is going to have a bond dipole that kind of points towards fluorine there. Fluorine being much more electronegative will hog the electron density. So this molecule is definitely polar. It definitely has a dipole moment because there's only one bond and that bond is polar. So it has this asymmetrical charge distribution. So any diatomic polar molecule like this is going to have a dipole moment. So we would say that this is certainly polar. Now, what would be the case if we had the fluorine molecule where F is bonded to F? Well, in that case, we don't have any polar bonds at all, right? Because both fluorines have the same electronegativity. So this bond is not polar. There's no bond dipole. That means that overall the molecule is nonpolar. Okay, but what about when we have larger molecules? Larger molecules can have polar bonds. For example, if I take the carbon dioxide molecule, it looks like this. Carbon and oxygen have very different electronegativity values. Carbon is more electropositive and oxygen is more electronegative. So I'm going to have a bond dipole on each of these bonds here. So if I look at the requirements for having a dipole moment, the first requirement is totally met. This molecule has a polar bond. It has two of them, in fact. Now, does it have asymmetrical charge distribution? Here's where VSEPR theory comes in. Since carbon has a substituent number of 2 and no lone pairs, it's going to be a linear molecule with a 180-degree bond angle. Because of that linearity, these bond dipoles here are equal in magnitude but opposite in direction. So they're actually going to cancel each other out. So even though it has polar bonds, those bond dipoles cancel each other out. Therefore, the molecule is nonpolar. So CO2 is actually a nonpolar molecule. It has no dipole moment. Okay, it has bonds, it has individual bond dipoles, but it has no overall dipole moment for that molecule, okay, because the dipoles cancel. Let me give you another example. Let's take BF3. So if I draw the Lewis structure for the BF3 molecule, looks like this. And this is one of those species where boron is electron deficient. It only has a sextet, but it's just a fine charge distribution. Okay, boron is very electropositive and fluorine is very electronegative. So we're going to have three polar bonds here, and we're going to have bond dipoles kind of pointing in all of these directions. So now we need to think about the geometry of this molecule. The substituent number around boron is 3. So this is going to be an example of a trigonal planar geometry. It's going to be a flat molecule, and all of the bond angles are going to be 120 degrees. So that means, imagine adding these vectors. If we did vector addition, those bond dipoles are equal in magnitude, and they're all pointing to the corners of a perfect triangle. So this is another situation where the bond dipoles are going to cancel. Okay, so this is a nonpolar molecule as well. So because it's a perfect trigonal planar structure, this molecule is going to be nonpolar. Okay, now let's think about another example. Let's take ammonia. So ammonia is NH3, and if I draw the structure for ammonia, looks like this. So this is a situation where I need to first assess whether there are polar bonds. Now, hydrogen is very electropositive, nitrogen is pretty electronegative, so there are actually polar bonds. All of these bonds are polar, all of these NH bonds are polar, kind of going towards the nitrogen. So there are certainly polar bonds, but is there an asymmetrical charge distribution? So here nitrogen has a substituent number of 4, but it also has this lone pair here kind of occupying space above this nitrogen where I've drawn it here. So this is not going to be a trigonal planar structure. It's going to be a trigonal pyramid. And the bond angles are going to be here, the bond angles are going to be slightly less than 109.5 degrees. And what that's going to do is give it an asymmetrical charge distribution. So that here, let me clean it up a little bit so you can see what I'm talking about here. If I add those 3 bond dipoles together, if I add those 3 vectors together, I would get an overall dipole moment kind of facing upward towards the nitrogen. So this is definitely going to be a polar molecule with a dipole moment. Okay, so the dipole moment kind of points towards the nitrogen because that's the most electronegative atom. So this is going to be a polar molecule due to its asymmetrical charge distribution. So that makes it very different from BF3. As a final example, let's look at water. Water, if we draw its Lewis structure, looks like this. And most students know that water has a bent structure and the bond angle is compressed a little bit below 109.5. So this is a bent structure. Does it have polar bonds? Certainly it does. Oxygen is very electronegative. So both of these bonds, both of these OH bonds are going to be polar. If I add those 2 arrows together, imagine adding those arrows together, I'm going to have an overall dipole moment kind of pointing up towards the oxygen. Just like in the previous example, ammonia, the overall dipole moment kind of pointed towards the nitrogen. So I definitely have both polar bonds and asymmetrical charge distribution in this example. So water is most certainly polar. Water is a polar molecule. Okay, so in order for a molecule to be polar, you must have both polar bonds in the molecule and an overall asymmetrical charge distribution due to its molecular geometry.